Do you think I'm being serious?
You get paid either way.
You're not going to be put in charge of anything then. Nothing would get done. All right. You want to do something easier or something challenging today? Oh, that wasn't one of the options. Easy or challenging? All right, let's do something easy today. Unfortunately, though, just like most of pre-calc, it's new stuff, right? So the challenge comes, can you actually, unlike what Winter's trying to do right now, can you actually pay attention to the whole class, keep your interest level high to understand this? There's nothing we're doing today that's challenging. It's all straightforward and easy. In fact, I could literally let Presley teach this because this is what she was doing 3 days ago. When I said, what are you doing? And she goes, I'm doing that thing with the circle.
Circles. I don't like circles.
All right, it's not a literal circle, but the symbology uses a circle. Okay. Why are you not clicking? Because why are you not clicking? Why are you not clicking? What the heck?
They want us to not work today. Are you recording?
I am recording. Well, this is weird. My clicker's not clicking. Ruh-roh, Raggy. I'm gonna have to do this by hand. All right. It's a sign that I need to teach the class. No. All right, write down your homework. All right, so I apologize for standing here for the entire class rather than moving around.
I've never seen you teach a class while sitting at your desk.
It just doesn't feel like you're teaching if you do that. Well, I have lots of button clicks, so if it was just one slide after one slide, fine, but there's things inside the slides to click. All right, everybody good? I said today would be long as you pay attention, it's easy. But it is new stuff. Ready now?
Yeah.
All right, here we go. Composite function is the name of the class, composite function. All right, pre-calc kind of like this is the thing. You're inside the car and these lions are hungry, right? This is pre-calc. If you decide not to pay attention, the lions are going to eat you, right? But if you stay in your car, you'll be fine. The lions are going to get into the car. And staying in the car in this metaphor right here is you got to stay engaged. You got to do the work. You got to study. You got to do your homework. If you do that, it'll be fine, right? You will pass. But if you don't do this, remember this semester now, you fail semester. If you're a senior, you don't even graduate now, right? So you got to stay on top of it, right? I'm not doing anything remotely that's challenging today. This chapter is kind of towards the end. It's a little bit challenging, but it's not that bad, right? But if you decide not to pay attention, their lions are going to eat you. All right, think about this. I have an assembly line, and it looks from the picture like they're making what does it look like they're making?
I thought she had a bucket on her head, but I didn't realize that it was.
What are they making?
Buckets.
They're making buckets. Thank you, Seth. Right? They're making buckets. So this is the assembly line that makes buckets. So the analogy is functions, right, in math operate like assembly lines. You have an input, right? Spheres. They go in the machine does machine stuff, and what comes out in this case are cubes. The machine stuff is that calculations. Take the x, multiply by 2, add 1. That's what's going on inside the math machine. So the math machine right here, I take my inputs, whatever the number may be, I multiply it by 2 and I add 1, and that's my output. So it's the same idea as a physical machine, these things called functions. We call the inputs not the inputs, we call them domains, we call the outputs range. Nothing new there. Okay. We define a function is that a mathematical operation where every input gets exactly one output. So if you put in a number, you can only have one answer. You can't have two answers. If you have two or three or four answers, you're not a function. You have to have only one answer. So you learned this in Algebra 1 and Algebra 2, but we're in pre-calc, so it won't be an easy thing. It's going to be a more challenging thing to do in pre-calculus. We learn more about functions in pre-calculus. So think about this. If I take one function, that's my analogy to it, assembly line, and instead of having one function, I instead have two or more functions, then together we call those, name of the class today, a composite function. A composite function is a function made up of separate functions that are put together one after the other. So if this is my analogy, guess what this makes? What does this make? Don't let Seth get the answer here. What does this one make? I took one function, that's that first assembly line, stuck it to the second assembly line. What does it make? What does the first assembly line make? What's the second one do? It paints it, gives it color. So what does this composite function make? You can figure this out. So what is the final output?
What is the answer?
Bucket cars. Really? What does the first function literally do? What's the second function do?
It's painting the
paints.
buckets.
What color does it paint it?
Blue.
So what does this thing do? So what does it make? It makes blue buckets, thank God, right? So we have an input that makes buckets in the first one. We take that input, we attach it to the second function that paints it blue, so we make blue buckets. Today we're going to do this, except they won't be assembly lines. They're just going to be functions. But the process is the same. You have an input, that's the raw materials, that goes into the first function, spits out numbers. You take those numbers and you put them into the second function, and you finally get more numbers that come out. So that's what we're doing today, and that's called a composite function. So here's it with math, right? We're not, in fact, making blue buckets now. We're actually making new numbers. But those new numbers come from two separate operations. In terms of this picture, the first operation makes a bucket. The second one takes whatever the input is and paints it blue. Okay, so that's what a composite function is. Hopefully you got that picture. Your book gives you this picture right here. So you have two functions here, G and F. The circle in the middle, which is what I was talking to Presley about, that circle in the middle, we've seen this before, except we saw it before when this circle was filled in and it was a dot. If it's filled in as a dot, it means literally multiplication. This does not mean multiplication. Guess what happens when we get to semester final? Somebody sees this and thinks multiplication. It's not multiplication. There will be multiplication on the test as well. But if it's an open circle, it means make the composite function. Okay, so confusing thing number one, symbology. Sometimes we say this is the fog, right? F-O-G. It's not. It's F composed with G. All right. Other thing that's confusing is, well, which machine comes first? The machine that comes first, the mathematical machine comes first, is always the second letter. The second letter is the one that you start with. In this case, that's G, which is why the input goes to the G machine first, spits out a number, and that number goes into the F machine. So the one that you always mess with first is what? The one on the left or the one on the right? The one on the right is the one that you always mess with first. So confusing thing number one, open, closed circle. Closed circle means multiplying. You're not going to see that today. You're only going to see an open circle, which means composite function. All right, confusing thing number three is the definition. So for those who get confused with words, I'm sorry, right? But here are the words. The words are given two functions, f and g. The composite function is denoted f of g, is defined by this equation right here. And what it's showing you is two different ways to write that composite function. Way number one is with the open circle. Way number two is just with parentheses. So we have two ways of writing the composite function, one with a circle and one with parentheses. Guess what you're going to have tonight for homework? Both of those. Sometimes they'll write it with an open circle. Sometimes they'll write it with parentheses. In both cases, which one comes first, the F or the G? The one on the right comes first. Now, you could write it any way you want. It could say G of F and then F would come first. And you'll see that today for homework. For homework's got like an A, B, C, and a D, right? A is going to be do F of G. B is going to be do G of F. C is going to be do F of F. And D is going to be do G of G. So you're going to see this in like 4 different flavors. Anybody really confused so far? All right. So baby steps first. Say again. Sorry. Good? Okay, baby steps first. Today we're going to do 4 things. Thing number 1 is evaluate. Simple. Thing number 2, compose. Sort of simple. Thing number 3, find the domain, not simple. Thing number 4, simple, but complicated. Right? The only one that's really hard is finding the domain. You got to think about it. If you actually do it, it's kind of medium, but you got to think about the domain. All right, let's do the 2 easy ones first. Evaluate and compose. Evaluate first. It's simple, right? Okay, so here's the setup. They're going to give you 2 functions. Yes, it seems like it's always F and G, but it could be any letters. They're going to give you 2 functions. You see the 2 functions? And then they're going to give you a specific composition. This specific composition is, I'm pointing to it, this specific composition is FOG, right? F of G, F of G. Okay, it tells you the order. And then it says evaluate both functions for the value 1, except it's not both functions. Remember the way the machine works. You throw in the input to the first machine, it spits out a number, you take that answer and you throw it in the second machine. So the question is, what's the first machine? G. It's always the second one is the first machine. So I take the value 1, clicking and nothing's happening. I take the value 1, that's the first machine, G. I take the value 1 and plug it into the X value for the G function. So in other words, I'm doing F of G of 1. So I do G of 1 first. Well, G of 1 is simply put a 1 where the X is, therefore that gives you the answer. So we're done with the first machine. The first machine we threw in a 1, it spits out a 4. What do we do with the 4? We throw it into the second machine, which is the one on the left. It's that picture right there. Okay, so we throw that 4 into the second machine, which is the F machine. So I'm simply, anywhere I see an X, I throw a 4. That's the blue one. And then I just go to town with the math. So therefore I get, do the math. Somebody help me. Do the math. 29. All right. Yes? You tell me, easy, medium, or hard. As long as you have the order right. If you get that order backwards, you get it wrong, right? But it's a pretty straightforward, easy situation. All right. Remember that picture. The machine on the right comes first. So the G comes first. All right. Hey, look, I just switched the letters around. See my composition? I'm not doing F of G, now I'm doing G of F. Should we get it's the same functions. Should I get the same answer? Probably not. It is possible to get the same answer, but probably not. I'm switching the machines around. So this time, which machine do I do first? I do the F machine. I'm still plugging in 1, right, to the first machine, which in this case is the F machine. So I plug in 1. Let's do the math a little bit quicker this time. And I get -1, which I throw into my second machine. And therefore, you can do that one in your head and you get -4. So we did not get -29. So it is typical that you won't get the same answer. All right. The other thing they're going to ask you, which is weird the first time you do it, and then it's not weird. We good on this one? The other thing they're going to ask you to do is, for instance, see what it says? See what it says? F of F, right? So we're doing the same thing only to one of the functions. We're still plugging in a 1. We're taking that output and putting it right back into the machine. It's like you got this loop. So there isn't two machines to consider. There's only one machine. So I'm going to throw in one. Well, we already know that answer, which is, we just did it. Sorry? Is it not? It's not the same function? Oh, it's -2. I see what you're saying. Yes. Sorry. So we throw in -2 and we get 5. Okay. Which we take in, plug it back into the same function, and we get 47. Okay. Does that make sense? All right. Do we need to do a G of G? Okay. One more, I'll do it really quickly. So now I'm not quite sure I didn't use -1 for the previous one. I used -1 for all the other ones. So G of G, we throw in 1, we get negative. Now throw in -4 back into it, and we get, say it. Okay. Was that too quick, or you got it? Complaints, anybody?
Which one is orange?
The yellow one.
The second one? So.
Well, technically, this first blue one that says G of -4 is -16. Technically, that's just evaluating the functions. So the composite function, it's the same answer, by the way.
So you want it.
Yeah, the yellow one is how you would write it. Say again?
If they gave.
All right, she's got it. Okay. Oh, so I said we're doing 4 things. I said the first 2 are easy. The first one's evaluate, pretty straightforward, right? It's pre-calc though, right? So they can give you some challenging stuff, right? You would think that you could, right? That answer right there, that there might be a way to do it on your calculator, and you would think you could do this on your calculator, and you would think you could do this on your calculator. You would not be disappointed because you can't do it on your calculator. All right, ready? Grab your calculators, except for Seth. Seth, yours absolutely will do it. I just don't know how to do it on your calculator. All right, so here's what you do. Step number 1, make that y1. So take that first function, the f function, hit y equals, and make that y1. And then drop down 1, make your y2 the second function, the g of x. You're going to y equals, you're going to make y1 the first function, you're going to make y2 the second function. Now quit. You got it. Now make sure you put parentheses. So the notation would be, well, let's see, we got to do f of g. Well, f was y1, so we need to do y1, open parentheses, y2, open parentheses, evaluate it for the number you want, which in this case was 1. And then since we had 2 open parentheses, we need 2 closed parentheses. And you should get, if you did it correctly,
What number are we evaluating?
1. Right here in yellow. And you should get, if you did it correctly, you should get 29. Vars, y vars, function. And then you repeat the open parentheses, and then repeat it for y2. Nick, you get it? Yep. Nick says you got 29. Yes? Anybody not get 29? Okay. Use that to your own peril. So when I get to a test day, I'm going to ask you to do it by hand, but you can clearly use your calculator to check your work, which is always convenient. You may have wondered, why do we need to have 2 machines when we could possibly get by with 1 machine? Is there a way to just make 1 machine to do the same thing? So if you were a company and you had 2 separate assembly lines, you would think someone would say, why do I need 2 assembly lines? Couldn't I just learn to connect the 2 and get 1 assembly line? That's what we're about to do. We give this a big fancy name, but what you're really doing is you're taking the 2 assembly lines and squeezing them together. In other words, I'm going to combine F and G into 1 assembly line. Well, how's that done? How's that done? Right? It's done by looking at what you start with, right? I knew you could do it. All right. It says f of g. So g is the far right one. If I took b, that's the 4x, and threw it into f, I would get f of g. So all I'm going to do is, whatever the order is, go to the right one first. That's the g. Take that function, which in this case is equal to 4x, toss it into everywhere you see an x in the first function. How many x's do I see in the first function? Just one. So everywhere there's an x, I'm going to write. Everywhere there's an x, I'm going to write 4x, right? This is called composite function, right? This is called the elegant way of doing it. You just make one function to do this. So in this particular case, f of g, right? I go to what? F or the g. I go to the g, right? I'm doing a composite function. So g is 2x plus 3. And I go to the first function, which is the f. And everywhere I see an x, I'm going to write 2x plus 3. But I need parentheses. So parentheses 2x plus 3. So I'm going to take that in blue, and everywhere I see an x in blue, I'm going to write parentheses 2x plus 3. So I see x twice. So if I put two parentheses 2x plus 3, and unfortunately it's pre-calc, right? They're going to give you a more challenging one. You got to do the math. Distribute the 3 and you get. Distribute the 3 and you get.
6x plus 9.
And then can anybody square 2x plus 3 in their head? Square the first one.
4x squared.
4x squared is how it starts.
6
And then you got to double.
plus 9.
Double.
So 12x.
Plus 12x, and then square the last one. Okay, so that's what she did. It's 4x squared plus 12x plus 9. And then distribute 3, we get 6x plus 9. And then combine like terms. The 12x and the 6x is 18x. The 9 minus 1 would be 17. And there we go. So there is your composite function in blue. They're going to write it like that in yellow. That is your composite function. Hey, now we only have one assembly line. Tonight for homework, they're going to say, compose the composite function. When you see that, they're asking you to take the two functions and make them into one function. Matt, what's the obvious question here? What's the obvious question? Nick, what's the obvious question? Great, we just did this thing. We got to an answer. The obvious question is, okay, not in this particular case. What's the obvious question? Why did I do that? Like, okay, great, I did all this. Why would you do this, right? You would do this because, hey, look, now if I evaluate the function for one, I don't have to do it twice. I only have to do it one time. So if you're evaluating, for instance, I don't know, 10 different values, then this method right here will save you some time and effort if you got to do it by hand. Now I just need to throw that 1 into 4x squared plus 18x plus 17 to evaluate the composite function for 1. Does that make sense? Like why this would be, I mean, I'm not saying you always need to do this, but if you had to evaluate it for multiple values, it would definitely speed up the process. Make sense? Okay. Here's an example. We're doing g of f. G of f. So which one do I grab? I grab f, which is, what's f? X squared plus 3x minus 1, and throw it into where the x is on 2x plus 3. So I go to the one on the right, which in this case is the f, that's the blue, and I'm going to throw it into the red wherever there's an x. There's only one x. I just need to put parentheses. So I'm going to throw in that blue into that g of x right there with parentheses. Distributive property? Somebody? -2. Oh, you did you simplified as well too. Oh, well done. I was just asking you to distribute the 2. Yeah, and then -2 plus 3 is 1. And they're gonna tonight for homework, they're gonna write the answer is this in yellow. Does that make sense? Okay, nothing challenging there other than a little bit of algebra. We okay, everybody? Evelyn? No, I'm just asking we're okay. All right, so if we look at our list, we've done evaluate, we've done compose. I said the only challenging one was find the domain. So if you were just cursory paying attention, now it's time to really pay attention. Okay, make sure you understand the logic of this. You ready, everybody? Really paying attention? Okay, it's not hard. You just got to understand the logic. Okay, so we're going to find the domain, right? The domain means what are the allowable x values? Okay, what gives us problems for domains? Two flavors. What gives us problems for domains? You can see one of them on the board right there. What always gives us problems? Fractions, not just fraction, but the denominator. Denominator can never be. What's the other thing that gives us problems? Square roots of negatives, right? Can't take the square root of negative unless we're going to go to imaginary land. Okay, so this one has problems. All right, so big picture, find the domain. It's what can x be or what can x not be. Okay, so let's see. Step number one in this process is you got to look at the order. The order of the function says f of g. So which one should I look at first? G. What's the problem with g?
X minus 1.
So g cannot be 1. Do you see that? Right. That's the order of the letters. Right. The first machine is the G machine. I look at the G machine and I say, well, geez, X can't be 1. Everybody got that? Okay, cool. So my domain for the composite function cannot include 1 because if I throw in 1, I'm immediately going to get a 0, no bueno. Right? Cool. You got to follow the logic now. You would think that the very next thing I would do is no. You would think, I just found what x can't be of my first function. You would think.
You would put a 5 to make it a 1 permanent.
Okay, she's already got it figured out. You would think we would do exactly, and Seth said we would do exactly the same thing with the second function, right? You would think that we should go to the f function now and say, what can f not be, Priscilla? And you would be wrong, right? Because Winter already had this figured out. Because think about how, this is not how it's done. We don't look at the second function and do what Priscilla did. But you would think so, right? Makes sense, right? So we take the second function, it sure says that x can't be -2, but that's wrong. Because we never throw in -2 into the second function. What do we always do? I mean, how does this process work? We throw in a number first to G. And G is the thing that spits out a number that we throw into F. So the question is, if -2 is the problem for the second function, how do we get to that -2? It's because of the first function. The first function can absolutely spit out a -2. Perfectly fine. But if the first function spits out a -2, that's what we're throwing into blue. If red spits out a -2, we got problems. So the question is, how would red ever spit out a -2? So how do we figure that out? We just not plug in a -2, we set the red equal to -2. So if we set the red equal to -2, I'm going back to the G function. If we set it equal to -2, that will tell me the x value that will produce the -2. Did you follow the logic of that? I can't plug in a -2 to the blue function. Everybody sees that, right? But the problem is, I do the red function first. So the question is, can the red function spit out a -2? That's what I'm trying to, well, it can. No, it can. And I'm trying to find out what is that number to exclude it. So I simply set it equal to -2 and I solve it. All right, what's the algebra involved here?
So because it's at equal, you move over to 2 and then you multiply -2 by x.
-1. So we clear the fraction first. So if I clear the fraction, it goes away on the right side, and on the left side, we're left with. Come on, do it.
2x and then 2.
+2. Now we solve for x. So -1. So -1 is the value of the red function that spits out a -2, which we can't throw into blue. That logic is the only hard part of today. You got to follow that logic. So the actual restriction on the domain are the two blue things right there. See the two blue things? So what are the two restrictions? X can't be 1 or -1. Once again, the logic is you go to the first function, you look at it and say what X can't be. But for the second function, what you figure out what it can't be, in our case, -2, you go back to the first function, set it equal to that -2, and figure out what X value produces that -2. In our case, that was -1. That's the logic. It's not crazy impossible, but it is a little tricky. Who's lost? Nobody? Okay. Usually I'll get a couple people that to do it, you get kind of lost on it. All right. So I think that's more of a wow. So we better do one. Okay. So here we go. Another example. Step number 1 is just look at what the composition is. What's the composition? F of F, right? So the first machine I need to look at is, well, F, the one on the right, F. So if I look at the machine on the right, which is the F machine, what can F not be? -2. Okay. So I can't be a -2. So X cannot be -2, but here's the problem, right? So you exclude that value. We go to the second function now. What can it not be? -2. That's what we set the first one equal to, because the first one can spit out a -2. Like the answer could be -2. I can throw in a number that's going to spit out a -2, right? I can't plug in a -2, but certainly that first function f of x can spit out a -2. It doesn't exclude -2, right? In terms of what the y value is. So I go back to the one on the left, right? I figure out what it can't be. It can't be -2. And I set the first function, the red one, equal to that. And then I solve it. This one's solved exactly the same way. It's just not as nice. Multiply both sides by x plus 2. So that's -2x minus 4. Add 4 and divide by -2, and you get -5/2. So I get two values that it can't be. It can't be -2, and it can't be -5/2. Once again, the logic. Look at your function on the right. In this case, the f function. Figure out what it can't be, -2. Then go to the left function, which in this case is exactly the same. Figure out what it can't be, -2, but go back to the one on the right and set it equal to that. In this case, this is this part right here at -2. So -2 can't be the right function. Solve that, and that will tell you what x value produces the -2. In this case, -5/2. Yes, no, maybe? Okay.
Is that it?
No, one last thing. All right. One last one of these. Okay, f of g. Which one do I look at first? G. G can't be -4. So -4 is half of the answer. Now we go to the right machine, which is f. F can't have not a -1, can't have a +1. Can't. I'm looking at the f function now, right? The g function, it can't be a -4. Now I look at that one, the blue one. Blue can't be a 1, correct? So I take that value right there, that 1, and I go back to the first machine, the red machine, the one on the right, and I set it equal to 1, because that's what I want to see, what would produce that 1. Well, what produces the 1 is the first machine, the one on the right. So I set that equal to the 1, and I solve that. That will be the x value that spits out a 1 in the red machine, or the first machine, the G machine. And she's getting 0. So I get x plus 4, so x cannot be 0. So if you throw a 0 into the red function, right, it spits out a 1, and 1 is what the blue function can't be. So I wind up with those two things in blue there. Now it's in yellow, what x cannot be. Yes? Good, everybody? All right. Last thing. All right. This is going to be show that two composite functions are equal. They're going to give you two composite functions. They're going to ask, are they equal? In other words, they're going to take the letters and they're going to mix and match them, right? I'm going to go to this right here first. Okay. So what they're going to ask you is f of g equal to g of f. And the answer is, if you do f of g and if you do g of f, and if you get the answer x, then the answer is true. Let me explain that. So here's my f function with numbers. Here's my g function with numbers. Look what happens when I take my f function and I throw in a 0. What do I get? 1. And if I plug 1 into the g function, I get, it kind of points back to what I started with. It points back to the x value. What happens if I throw in 2 to f? I get 3. Take 3 to the g and it goes to, so if it produces the initial x value, well, then they are in fact equal functions. Like you literally get exactly the same thing. So bottom line for us, for the very last thing, are two composite functions equal? You just need to see if they equal x, which sounds pretty straightforward and easy, and it is in the sense of what to do. It's just that doing it requires a little bit of algebra. So bottom line for us, they're going to ask you whether f of g is equal to g of f. You're going to do that composite function. If you do that composite function for both f of g and g of f, if you get to the answer x, then the answer is yes. If you don't get to just x, then the answer is no. So let's see how that works. Doesn't matter the order you do this. You can do g of f or f of g first. It doesn't matter. I'm going to do f of g first. So I take g. G is x plus 4 over 3. And I throw it in to f. I'm like doing that composite function. So I took this, the x plus 4 over 3, threw it into the x value of the f function, and then I do the math. Well, 3 divided by 3 cancels. So I'm left with x plus 4 minus 4, which is clearly x. Now, if I can get x for the second way, the g of f, then the answer is yes, they are equal. So let's see what we get for that. Now I'm going to do g of f. I always start with the one on the right, which is f. Now I'm going to throw f, which is 3x minus 4, into g and see if I get x. Okay, so there's only one x in g. I replace it with 3x minus 4. 3x minus 4 plus 4 is 3x. Therefore, I get x. And therefore, your conclusion is, yes, they are equal to each other. When this goes wrong, then you're going to be left with, I don't know, x plus 1 or something other than just plain old x. Leaf, you with us?
How would you do that?
Which one, right or left?
Left.
On the left side? So it says check out f of g.
Yeah, just.
So I start with g. G is x plus 4 over 3. Oh, well, 3 divided by 3 is 1. It cancels.
Oh, 3. How? Because the bottom one isn't being.
Sure, there's a multiplication right there. If you'd like to use the distributive property, you could do that. That would give you 3x plus 12 over 3. 3 goes into 3 once, 3 goes into 12 4 times, so it cancels. Okay, yes? One more? Yeah, one more. And then the bell's going to ring. Okay, all right, same thing. If they are equal, f of g and g of f should produce x. Doesn't matter the order that you do them, you can do f of g or g of f first, but we will always start with the one on the right, which in this case is g. Well, g is 1/2 x. I take that and I plug it into f. Wherever I see an x, I'm going to write 1/2 x. Well, clearly that gives you x. Everyone was saying x except you, Evelyn. You say 1.
Oh. Well, it does equal 1, so.
1x. All right, but that's not conclusive proof. We also got to do it for g of f. So this time we plug in f, in this case 2x, to this one, and that's kind of clear as well too. And it does. So our conclusion is yes. Yay! That's the whole class. Not bad, right? This chapter is a little medium at the end, but it's not a horrible chapter. You remember doing logarithms in algebra 2? Logarithms?
I love
Yeah,
it.
this ends with logarithms.
Are you sad?
Sad? No.
Reading letter.
Well, of the first semester, no, I'm happy about that. Oh, I am sad, and I will say that the longer you teach, the more you realize when you teach high school, it's like, wow, I'm not going to have the pleasure of being with you, in a classroom at least ever again. So yeah, that's kind of sad, right? But in terms of woohoo, it's almost Christmas, it's Thanksgiving in a week, heck yeah, I'm happy about that. What's the yeah, I'd say that. Of all the years, you have the most personality, right? Both good and bad. I mean, if you think about some of the characters we've had in our class,
Like who?
well, you weren't around for Chris, were you? Oh, I'm recording this. I better stop. No, but